Okay, so let's pick up where we left off last time. We might end a little bit short today. I have a meeting I need to get to, and I have to commute. But we'll see. We'll see where we end up. Okay, so we started talking about assembly language last time, and you had a homework assignment to swap some values. Should not have been overly difficult. We'll see some examples today that sort of kind of do the same thing or something very similar. So if you look through the slides, you would have hopefully seen that wasn't a big deal. So let's talk a little bit more about, what's the role of assembly languages. Traditionally as a computer scientist, we're going to be using a high level language like C, C++, Java, C#, whatever, to do a majority of our programming. Ultimately, the computer speaking machine language, binary. So I think this give me, we'll get to that. So when we write our high level code, we compile it. We talked earlier in the semester about why does a compiler need to target an architecture as well as an operating system? Well, the architecture side of it is what we're talking about right now, and that is the assembly code for the ARM processor. The operating system would be a separate piece from that, but also that's what a compiler would need to target. So ultimately, even if we are not spending tons of our time as computer programmers or computer scientists writing assembly code directly, the compiler that we're using to communicate with our high-level language it's ultimately outputting this type of stuff. So therefore, it's kind of important for us to understand what does our high-level code that we write ultimately turn into at that low level. So generic syntax for a ARM instruction, you've already looked at these, I'm sure, with the homework, is you're going to have some sort of mnemonic. So what's the command you're issuing? There might be some conditionals. There are some suffixes in ARM that we'll look at. And then you can have some operands. Typically, you have your destination first, and then you have a first and second parameter if a second parameter makes some sense. And here are not necessarily an extensive list of ARM instructions because, we have a couple of different modifications on the ARM architecture, but this is a reasonable list that gets us maybe where we need to understand. So a lot of the things that we're doing, and you kind of see some kind of double moves here. So one of the things that's kind of common among assembly instructions is they only do one thing. Like when I first introduced, what is the processor? How does it work? We talked about it like, if you put your hand up, you wiggle your thumb, that doesn't do anything special. You move your finger, that doesn't do anything special. But you start doing those things in order and together, you can accomplish real tasks. So typically when we think about assembly, we're thinking about, a very small number of tasks that aren't all that interesting in and of themselves. But as we go through this list, we start seeing that there actually is some double dipping in some of them that, maybe is something that's kind of a common thing. This is becoming more and more, we're more and more able to do things like this because of our updated way that we're making our computer architecture. I think we talked before with processors that, you have various nanometer technologies, and you might have 5 nanometer technology or 3 nanometer technology or 15 nanometer technology. And that's really, excuse me, that's really talking about the ability we have in our manufacturing process to print circuitry how close can we put circuitry to get next to each other before it becomes a conflict? So the better we get at that manufacturing process, the more stuff we can fit in the same space. So as we've gotten more stuff in the same space, we have some flexibility to add some extra things. Obviously, then pushing that up against the constant concern of heat. And that becomes kind of an interesting thing with our, newer devices where, geez, we are trying to deal with heat in a silent way. One thing you've maybe noticed over the last many years, if you're certainly your laptops, is there's fewer and fewer fans inside of laptops. I'm not sure we ever had fans in our smartphones, which is why our smartphones have historically done less than our laptops, although now that line's getting a little bit blurred. So either the processors that are sitting inside of our phones are significantly less powerful than what's in our laptop, which is commonly true, or in many cases, they actually lower the clock rate of the processors in some of these mobile devices. And when we say lower the clock rate, what we're really saying is reduce the number of instructions per second that the processor can eat. Because every single time you fire electricity through one of these magic tricks, heat is produced. And the more heat that is produced, the more problem that we have with the device, whether it's burning your hand or causing heat damage potentially to other parts of the device, so on and so forth. Similarly, not just with the heat production, but also the electricity use. So the more instructions that we call every single second, the more energy that's going to be used as well. So there is, and it's kind of an interesting trade-off between desktop computing and mobile computing, is that in desktop computing, we typically, we sometimes will laughably compare the efficiency, the power efficiency of various processors or graphics cards or whatever it is. But largely, this is more of a measurement of how big of a power supply do we actually need to power this whole computer. If you are running a relatively common business office machine, you're not going to be running the overclocked processors. You're not going to be running the latest greatest giant graphics card. You're going to have a much smaller requirement for electricity. Oh, I need to get some coffee in this machine here. I don't know why I'm yawning so much. I actually slept really well last night. So, yeah. So with a desktop computer, we're not really thinking about that power efficiency for real reasons. On a mobile device, for reasons we've already discussed in previous classes, what we really do care about that. So sometimes we're not taking full advantage of the architecture that we're dealing with. We're going to be talking about some virtual reality stuff here pretty soon. And one of the examples we're going to bump into, and you can think about, some of the newer VR stuff are basically standalone VR headsets. You can really start off by thinking of them like a smartphone. Because that's effectively what it is. It's a smartphone with, instead of your normal screen, it's got two eye things, and you snap it to your face. That's what a mobile VR headset is. We put some good software inside of it, and cool stuff happens. But the most popular one of those these days is something called the Quest 2, and the Quest 2 has a Qualcomm XR2 processor in it, but it's underclocked. So that processor is actually capable of more than what it's currently doing. But if it does more, it's going to give off more heat, and overheating could cause a problem, especially when you have all that stuff that close to your eyes. You're going to start feeling the heat. Maybe the lenses fog up, all sorts of stuff. There's things we don't necessarily commonly think about that's related to heat in a mobile device. It's not all about battery life. Especially as we're starting to think about wearable devices. Now I just was reading an article yesterday about augmented reality contact lens. You know, these are going to be things that are going to be real in the next decade. You know, right now these are prototypes, so I don't think you're going to be finding it at Best Buy next week. But you very likely will be able to buy one in 1 to 3 years, and they might be very commonplace in 7 to 10 years. Where everybody's walking around with their contact lenses, whether they need a prescription or not, and seeing the whole world augmented. But the point is, you start thinking about now, especially with a contact lens, you don't want that thing giving off tons of heat. Those decisions really are meaningful when it comes to mobile computing. So in any case, just kind of keep that in mind when you're thinking about the trade-offs that have to occur in the mobile world, because we really are solving a, I don't know about harder problem, but it's definitely a different problem. As software engineers who are more commonly making things for mobile, and really think about that. I mean, when we say computer today, and I think I mentioned this in one other class, 20 years ago, if we said, just go to your computer, we were effectively talking about going to your desk where you have your big desktop tower or whatever with your big monitor sitting in front of you. That's what a computer is. When somebody says a computer today, I'm guessing most of you think something along the lines of a laptop. That's what we consider a computer today. Now, that doesn't quite have the same decision making that we have in the mobile device, the phones and things like that, but it's not that dissimilar. I mean, we are making battery life decisions, heat decisions, because these things are going to be sitting on our lap or whatever. It matters. It matters the amount of electricity those things are using and the amount of heat they're giving off. So this is really commonplace for us today. And as a computer scientist who's effectively wielding the same high-level programming languages, if we just think from the software perspective, we're wielding the same high-level programming languages that we did 20 years ago, maybe some updates or whatever, but largely the same kinds of stuff. It's really those compilers that sit in between us and the hardware that translate whatever we just typed into appropriate assembly language for that underlying architecture. And part of what that compiler might do is it might make decisions that take power consumption and heat dissipation into consideration, not necessarily always producing the most optimal code. So think about if you were writing a compiler, how difficult that might actually be. Compilers are kind of difficult to begin with, that you're trying to take somebody's high-level program and turn it into, at the worst case, equivalent I guess equivalently accurate low-level code, with the best case being, hey, let's optimize it a little bit. I sometimes will say something along the lines of, a good compiler makes a bad programmer look better, at the assembly language level, something like that. So that's already a hard enough problem in and of itself. Now we're asking our compilers to make an additional decision. And some interesting stuff that's already starting to happen. I mean, you're seeing it in hardware all over the place these days. We talked about, I don't know, several classes ago when we brought up all of Apple's, the AX processors and the M1 processors, and all of them had some number of machine learning cores in them. And right now, that phrase almost feels like a buzzword. Like, okay, well, what are we really using the ML cores for? And we are using them for some things, but I think that is going to become more and more of a necessity whenever you see something about machine learning. What you really should be thinking about is a processor that is solving problems differently than other processors. These are cores specifically towards a neural network that's trying to make more human type problem solving. That doesn't necessarily mean better problem solving. Really, the best way of thinking about it is that it's different types of problem solving. Humans are very good at solving certain kinds of problems relative to a computer. Computers might be better at solving other kinds of problems. The same thing is true with quantum computing. That's probably a phrase that all of you at least have heard, whether it was on some sci-fi show or something like that. You heard it referenced as a quantum computer. Well, quantum computers are not going to be the replacement for our, what in quantum computing, they typically call it classical computers. They're not going to replace it. It augments our ability to solve problems. A quantum computer, because of its nature, because of kind of how it works, and we're not going to go far into that here, but because of how it works, allows certain problems, interestingly so, problems that happen to be very difficult for classical computers to solve. A good example of that, maybe from your undergrad, is the traveling salesman problem, TSP. The traveling salesman problem is a common computer science problem that deals with, you have this salesman who lives in one city, let's say, and he needs to travel to 10 other cities on his route every single day to sell his encyclopedias or whatever he's selling. And the idea is, what's the most efficient way to visit all those towns and return home at the end of the day so that he travels the least amount of distance, or it happens in the quickest amount of time, depending on if you're measuring speed versus distance, whatever it is. That's actually, it sounds like it's not that bad of a problem, but think about it. If you were solving it as a human being, you almost have to create every single permutation of your trip and then decide, okay, well, what's the best route? What route do we go? So now to write an algorithm that's attempting to solve that same thing is actually pretty difficult. And it's really not that dissimilar to how we might just do it as a human being. A famous algorithm for approaching the traveling salesman problem is something called Dijkstra's algorithm, which is it's a greedy algorithm that basically just tries every single permutation and takes a couple of little shortcuts here where it bails early when it notices one permutation is just not going to work out. But at the end of the day, it's not significantly better in terms of speed. Well, quantum computing, it's like kind of made for that type of thing, where you can solve problems like that very, very, very quickly because of the nature of how reading qubits, quantum bit is either on, off, or spin, the nature of how quantum works. And we can't even explain half of it, but the point is that we really, with quantum computing, we can measure all possible outcomes in a single read. Kind of fascinating stuff, but you see that particular kind of problem is a problem that lends itself to that type of problem solving. It doesn't lend itself to most of the classical computing stuff that we do today. So it's not going to replace our laptops. We're not going to be running around with quantum computers in our lap. We might sometime in the future, my wife just spilled water. Sometime in the future, we might have quantum cores or a quantum subprocessor or something like that in our laptops, or heck, it's going to end up in our phones and things like that too. Those might be realities. Right now we have machine learning cores that are in there, and that's helping us solve some problems that are a little bit more human-like decision making, that just are almost hard to explain. If you go back to the very first week of class, one of the things I probably said, I like to go back to that slide of how do human beings solve problems, yada, yada, yada. And one of the things I typically say there is the challenge of a human being telling a computer what to do is that we are so good at solving problems as humans that we have trouble articulating how we solve them. And if we can't explain how we're solving a problem, how do we expect a computer to be able to do it, because it's only following our instructions? Well, when you start getting into machine learning stuff, now all of a sudden the way you're telling a computer, maybe we say teaching a computer how to solve a problem, is you're giving it inputs and you're giving it the expected outputs, and then you're tweaking things in the middle to get it to kind of balance usually what's called a machine learning model or a neural model to produce the correct outputs. You're not necessarily telling it how to do that. You're hoping that it kind of somehow evolves into the correct, let's call it solution, but solution has a pretty vague meaning there, where it now does solve the problem correctly. Completely, a lot of times I'll call neural networks a black box, because we don't actually know what's going on inside of the neural network, only that You give it certain inputs, it's giving you an output that's correct, and you don't know why, just that it's correct. So we're augmenting our computers with all sorts of things like that, which allow us to solve different classifications of problems. All right, so in any case, if we're just focusing on the, let's call it the general purpose instruction set for ARM assembly, and this is kind of your common move in any sort of assembly, you're always moving data around. So you need to have the ability to move stuff from one hardware register into another hardware register, to move one immediate value like number 7 into a hardware register, something like that. A combo move that we see here in the next one is like move and negate. So sometimes you need to multiply something by -1. That might be your very next instruction. If you didn't have this this hack here, you would probably need like 3 or 4 instructions to ultimately do a multiply by -1 and get the value stored back into the target destination register. So this can actually be a pretty powerful little magic trick here, because it is allowing you to effectively compress, let's just call it 4. I mean, I have to think through it how many it would actually take, but something in that ballpark. 4 individual instructions into a single instruction. That's pretty powerful. Add, subtract, multiply, these are obvious. We need to be able to do math, because at the end of the day, math is kind of the thing that our computer most, does all the time. And we just have to figure out the various interesting problems we can solve while harnessing that. We talked, I think last class or the class before, about shifts. So logical shifts left, logical shifts right. These are bit shifts. So we were talking about those bitwise operators. Logical and arithmetic. Let me see if I can give you an example. Well, let's not give you an example. I don't want to burn time with that. Just those are bitwise operators. Rotate right, also a bitwise operator. Compare, this is effectively our if statement. When we talk about that slide of how do human beings solve problems, we remember stuff, we ask questions and repetition. And they said something like 100% of programming languages have facilities for these things. Well, we have facilities to remember things with assembly. We have facilities here now to ask questions with the compare operator. And I'll show you, well, that's the compare operator along with these branch operators that allow us to jump, but these branch operators also help us with our loops, our repetition, because we can branch back up to a higher place in our program list. Here's your bitwise ands, bitwise ors. We talked about that. Bitwise zors or xors. All right, so these next two are our famous assembly instructions, loads and stores. A lot of the time, and we talked about the nature of memory in our processors, where the closer you get to the CPU, the faster and smaller typically the memory gets. So when we're sitting right next to the CPU, we're dealing with the hardware registers. Those tend to be the smallest little buckets, but they also tend to be the fastest. So most of the data that we want our processor directly working with, we want it working directly with those hardware registers. So that means that a lot of our ninja moves leading up to our processor actually doing something is going to involve getting stuff from slower memory into our faster memory. Moving something like maybe from your system memory, which is like your 16 or 32 gigabytes of RAM in your computer, or 8 gigabytes of RAM in your computer. Even if you're on what we would call a relative budget pleaser computer today that has only 8 gigabytes of RAM, imagine like what we were talking about last class, where you have 8 gigabytes of storage here versus 32 bits of storage here in a assembly instruction. That's, or in a hardware register. That's drastic size difference. So because of that, it makes a whole lot of sense for us to store a bulk of the data that we have long-term storage in system memory. Well, longer-term, short-term storage, let's say, in system memory, and only bring it to the processor when we're ready to directly use it. And that's what these load and store instructions are for. It loads something from system memory into a hardware register. or it stores something from a hardware register back into system memory. So these tend to be bread and butter commands in all assembly languages. Same thing with move. All right, so load and store, those are get stuff from system memory onto the processor. All day long, every assembly language has equivalents to those guys. For cheating here, we also have the ability to load and store multiple values. So instead of having, if you want to load 3 different values from memory, actually just go 2 different values. I'll have to see how extensive this goes. But if I want to load 2 different values from memory, well, I can do that in 2 separate lines, or I can do it in a single line. Well, there's an efficiency built into that if I'm doing it in a single line. And because loads and stores are so commonplace, it makes some sense to have that kind of to go ahead and build in the extra instruction to do that. A lot of processors, most of our modern processors also use a stack. And the stack might be implemented inside of system cache. It could be implemented in system memory, but it's effectively a stack data structure, which is a first in, first out, like a stack of magazines, or the last in, first out rather. So the last thing you put onto the stack would be the first thing that comes off the stack, that type of thing. And there's all sorts of logic where stacks are incredibly beneficial. So sometimes you might want to, put data that you're going to need soon, but don't need immediately. You might want to throw it onto the stack quickly so that maybe it's like a function call. You might push the 4 parameters to a function call onto the top of a stack and then burn them when you're actually processing. Pop from the stack into a hardware register and do your stuff with it, rather than moving that data all the way back to system memory. So as we're talking through this, really try to think about, at the assembly level, what are we actually doing? It's what memory are we reading and writing stuff to? And then what are we doing to it? It's a fairly trivial thing that once you see the output of your compiled programs, it becomes, intimidatingly boring. It's just a zillion lines of moves and loads and stores with some adds and multiplies and things like that. But it's really just a whole lot of moving data around and doing some math with it. And that's where it relies on the operating system's magic tricks to leverage some of those things that have already been written. And hopefully we can, when we're done talking about this, we can kind of respect what those operating systems are doing, because somebody had to write that operating system. And at some level, they were probably writing aspects of the operating system in assembly language to actually, when we do a syswrite, for example, we looked at the Linux Hello World program. If we do a syswrite, which writes, like, I think we looked at hello world out to the screen, it was a little bit intimidating looking, but it wasn't a super long program in assembly, because we were leveraging the operating system's program called syswrite. Well, syswrite ultimately is a bunch of lines of assembly code. So what if you didn't have syswrite and you had to write all those lines yourself? And by a bunch, I mean probably, hundreds of lines, very potentially hundreds of lines of assembly code. So it would make that little program that didn't seem that bad, but still seemed cryptic, way, way, way worse if we weren't leveraging the operating system to do it. So some smart people who wrote that operating system did all that heavy lifting for us so that we don't have to, and we can just now, even at the assembly level, we can leverage that operating system as if it's a power tool. Kind of a fascinating thing. So these push and pops on the stack are, again, just moving stuff between 2 memory locations. So moving stuff between memory, moving stuff between memory, moving stuff between memory, doing bitwise operations at a particular place, direct comparison of 2 locations in memory. Let's see, these are all bitwise operations, doing math with things that are currently sitting in memory and moving things around in memory. Just think about how boring all those instructions are. They're just moving stuff between places in memory, a high percentage of them. Then we get to all these branch instructions. When you see a branch instruction in assembly, typically that is a go to another place in the program. That's what a branch typically does. So a branch is probably going to follow like a compare. You might compare a couple of values, and then you're going to branch to a different, potentially branch to a different location in the program. I think we're going to see an example of this in a few minutes, maybe. Potentially branch to a different place in the program, depending on what the result of that comparison was. So we can branch directly to a label somewhere in the program, so we can just kind of mark where we want it to go to. I'm not really sure what a branch with a link is. Branch and exchange swaps two things. Same problem here. And then here we have a built-in thing for making system calls. If you remember back when we were looking at our Linux assembly, in fact, let me bring that up here. Linux hello world. I misspelled it, but it should bring it up. You know, this is i386 assembly instead of ARM assembly, but we see here's a whole bunch of move stuff. And then right here, this is when we're calling upon the kernel. Okay, so this is kind of having to know this knowledge about this is the place in memory where the kernel's like start program is living. So when we interrupt the processor and tell it to go to this location, we're effectively saying we have knowledge of where the operating system lives, the operating system's loader lives, and we're telling it to go and do something. Okay, where here we can actually go ahead and directly call a system call from our operating system, so the two can work closer together, even though under the hood, the same thing we just saw is actually happening. Okay. So like we just talked, these load instructions are kind of our bread and butter, moving stuff from system memory into registers, or moving stuff from, or storing stuff from registers back into system memory. So even though as human beings, we think of system memory as being very, very, very fast, as computer folk, well, at the assembly level, system memory is the slow guy. You know, much slower than our L1, L2, L3 cache, or than our registers. Certainly registers are the fastest. All right. So that's what's happening with these load instructions. Now notice they do it like, so if we do load into R2, remember we looked earlier at the syntax for a ARM instruction. The very first thing that's in there, well, we have our mnemonic, then the next thing is our destination. So we're going to load something into register R2. And what are we loading? Well, the original address is the value found in R0. So in brackets here, so typically when we see brackets, we're talking about a memory address, something like that. So R0 is the name of a register. So presumably what would happen here is we would load into R0 an actual system memory address. And then this would say load into R2 whatever's found at that address. Similarly, if we're going to store whatever's currently in R2 into a place in memory, we're going to store the current value of R2 into the memory address. So that's what the square brackets are for. And then the actual address would be stored in R1. That's where we're going to in memory. And at some point, I think I mentioned, so if we talk about what's a memory address is just a number. You know, when you think about your system memory in a computer, think about it as one big long street. Okay, so that's house 0, house 1, house 2, house 427,938, so on and so forth. So what kinds of values are we storing in R0 and R1 here? We're storing just the number. You know, it's going to be some 32 or 64-bit number. And we're saying go to that street number. So a lot of times when we see the word address, we get freaked out when this is just a number. This is saying go to memory and go to this house number or this bucket number. Same thing up here. Okay, so pretty straightforward. We load stuff from memory into a hardware register. We store stuff from a hardware register back into memory. Okay, So here's some functional assembly language using ARM. So this is similar to our little hello world thing. So we have a couple of, so we have a data section, just like we would have in Intel assembly. So we have a couple of variables, var1, var2, you know, and these guys are going to be, they're going to hold the number 3, hold the number 4 in this case. We get to our start functions. This is kind of like main in our C program. So this is where the program actually lives. So we're going to load. Remember, loads go from memory into a register. So we're going to load into a register whatever lives at the address of var1. And notice down here is the address of var1. So address to var1 stored here, address to var2 stored here. So these are memory addresses, where a memory address is just a number. You know, even though, and this is where people get freaked out with computers, when you see a memory address, a lot of times you're seeing those weird looking cryptic hexadecimal values. Well, remember we talked about in here, the reason we use hexadecimal is, well, A, it has a lot of compatibility with binary, right? You can store the entire hexstat bit space in 4 bits. It's 4 binary bits, so you can easily move between binary and hexadecimal. So that's the first perk. But from a human being perspective, why is hex better than binary? Well, if you have 32 gigabytes of system memory, that means that you have houses on this really, 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 really long street. And if you need to get to some house way, way down that street, and you're trying to, you know, you're indexing the street, this is house 0. So if it's 32 bits, it's going to be 32 zeros. House 1 will be 31 zeros followed by a 1. House 2 will be 30 zeros followed by a 1, then a 0, so on and so forth. So when you get way, 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 way down that street, I mean, well, even early on in the street, you're using 32 zeros and 1s to represent your value. And if it's 64-bit memory, it's even worse. All right. In hexadecimal, we can represent the same magnitude, the same number. Just like we can write the decimal number 127, we can write that in binary, the equivalent in binary, the equivalent in octal. All right. So really large numbers, when written by human standards, let's say, when written in hexadecimal, have a smaller footprint. So it's actually a compressed way of representing the same magnitude. All right, because the number 127 in decimal is going to have its identical equivalent in octal, which is going to look a little different, but it's still the same value because we're just we're encoding it in the octal numbering system versus the hexadecimal numbering system. So at the end of the day, what does hex give us? It gives us a relatively small footprint way of representing larger numbers. Because a hexadecimal value for a really big number is going to take up less characters, let's say, than the same number in binary. If we just look at the extremes. All right. So when we talk about a memory address, people get intimidated so quickly. All it is a number, just labeling which house in memory you know, when memory is one big long street. So our computer memory is way simpler than our addressing in real life, yet we're so used to how real life addresses work. You know, 123 Elm Street in Mequon, Wisconsin, 53097. You know, there's a lot of pieces of information that I just spit out there. And for a human being, you just take that for granted because you've been doing that your whole life. Rather than assuming that we all live on one gigantic street and we say, yeah, just go to house 204. And you just mosey on down the street, counting house by house by house until you get there. That's how computer memory works. It's simple. All right. So the fact that it's a hexadecimal number can look intimidating, but actually is just a number. So here at address var1, address var2, we're just storing 2 numbers. Which house in memory do these 2 values live in? All right. So we're going to load into R0 the value. Actually, we're not loading the value. We're loading into R0 the address of R1. I talked about this in the previous slide, but we'll see it again here. we're loading into R1 the address of var2. So both of these are just memory addresses. So R0 holds some number, R1 holds some number, and those numbers happen to correlate to an address in system memory. All right, so that's what we're loading into those two registers. Now we're loading into R2 the value found at that memory address. So R0 holds a memory address. R2 is now going to hold the value, that's where the square brackets come in, the value that lives at whatever address R0 is. We're going to store the value that's currently in R2, which is the value of R0, which is the variable 3. Okay, so the var1, which is the value 3, which lives at the address of var1 in memory, that's what's stored in R2 currently. We're going to take that value and we're going to push it out to system memory. We're storing it into system memory. Where are we storing it? Well, we are storing it in system memory at address, wherever the address of var2 is. All right, so this is an example of a program. This is going to be similar to what you wrote for your homework, where we read something in, we're effectively copying the value of var1 into the value of var2. We're overwriting this 4 with a 3. That's what this this code ultimately does. Okay, so for your assignment, I think you were supposed to swap the values between like 3 different variables. You would have just done these things, with a little bit more gusto. You would have had a few more lines to do the various swaps and stuff like that, kind of moving stuff into system memory and back out of system memory, using normal variables to temporarily hold values so that you can ultimately overwrite them into some other place. Questions about this? I know this kind of code can look intimidating, but again, just think about how simple each of these lines is. We're just moving stuff between system memory and hardware registers, or from hardware registers back into system memory. It just so happens that the places in system memory are the house address, the memory address of where these variables are actually stored in system memory. All right, so this is kind of getting closer to what we looked at last time or 2 times ago when we did the bit shift stuff, but just to kind of give us some graphical versions of this. We see that we have these, this R0, R1, R2, these are all hardware registers. And right now, the values that are in here are actually represented in hexadecimal. All right, so that's what's in here right now is hexadecimal values. And this is kind of showing us a picture of our of the program from before. So notice here in our system memory, so this image here over down here in the bottom right is a picture of what system memory might look like. And we see that the value of var1 is a 3 and the value of var2 is a 4. Value of var1 is a 3, the value of var2 is a 4. So these live somewhere in system memory. All right, so those are the 2 values we're storing. And yes, they're stored in hexadecimal, but the number 3 in hex is the same as the number 3 in decimal. Okay, so we're okay, we haven't broken anything. All right, and it just so happens when we put those into memory, these are the memory addresses that were assigned to those guys. So this is house 000100090 hexadecimal, and this happens to be his next door neighbor taking 32-bit steps because it's 4 bytes difference, 0 to 4, 90 to 94. So this is house 000100094. Doesn't really matter what these numbers are. These are just locations. This 3 lives in system memory at this place. This 4 lives in system memory at this place. All right. So what did we do? We loaded into R0 the address of R1. So R0 holds this value right here, the 000100090. All right, that's what we loaded into R0. This guy right here. We loaded into R1 the address of R2, which is the one ending in 94. So R0 holds a memory address, R1 holds a memory address. Then we load a value into R2. That is the value that lives at the memory address stored in R0. So R0 holds this memory address, the one ending in 90. So here's that memory address. Here's the value at that memory address. So we load into R2 the value that lives at this memory address, which is the 3. All right. Then we went ahead and we stored the value that's in R2, which is R3, into the memory address that was R1. R1 is the 94 right here. So they haven't shown the result of that, but this last line will take this number 3 and overwrite memory address 94 with it. So we'll end up with a 3 right here after that last line of code. All right, so this is a pretty good visual of what was happening on the previous slide. So any questions about that one?
I brought this up in chat, but I just linked to where that diagram is, and it actually shows you, like, so right now the picture you took is actually like in the middle of its process, but it actually does like show you what the code's doing. So if you wanted to see a more live version of all those steps going through, you can take a look at that.
Oh, you put a link in chat is what you're saying.
Yeah.
Yep.
That's where the diagram is located.
Sure. Right.
I just thought it would be easier if you were more of a visual, or you could see that in more action, because it actually goes through it step by step.
Yep. Yeah, so this picture, like he's saying, this picture only takes you through the first 3. It doesn't actually do this last step follow through. So if you want to watch it, there's a thing over on the link he gave. Okay. So this was your homework for today. So write some assembly code that loads those numbers and then reverses those numbers in memory. Let's see. This kind of stuff we just looked at. This is something we talked about a couple of classes ago where we can break down. So here's an example of me having a single hardware register storing 8 separate variables in there. So we talked about how do you play around with bit space? You know, hey, I have 32 bits to mess with. How I choose to use those bits is up to me. You know, I can store the number 2 in 32 bits. That's going to be 30 zeros followed by a 1 followed by a 0. Well, I'm wasting a majority of that bit space because I'm storing such a small number. So I can choose to use that bit space to store bigger things, and through the use of bit shifts and bitwise ands and ors, I can kind of accomplish that when I put stuff in or I extract stuff out. Kind of interesting tricks you can do with bitwise things. All right, so that's kind of what this slide is talking about, that magnitude versus bit space. The size of a value versus the almost like the size of the yard we're dealing with. All right, so if you have a humongous value that's going to use up 32 bits of memory, you know, so the largest unsigned value that can live in 32 bits is like 4.2 billion or so. Well, if I'm going to store the number 4.2 billion, I need to use all 32 bits to do that. But if I only need to store the number 100, or I need to only store the number 1 billion, I don't actually need, well, actually I'll need most of those bits. If I'm going to store the number 75, I'm only going to need the first 8 bits, let's say 7 bits I can get away with, but 8 bits. So I have plenty of real estate I can use to do other things with if I know exactly what I want to store. So I think I refer to this as bit slinging. So kind of taking advantage of our knowledge of those bits and not getting intimidated by the fact that, oh, this is a hardware register, it holds binary stuff. Binary stuff is scary, all those things. It's so easy to get intimidated by this stuff when it's so much simpler than how we operate in real life as human beings. Yet in real life, we're so used to it that it's not intimidating to us. Just kind of a funny twist around type thing. So let me jump ahead a little bit. Okay, so I'm gonna unlock this next assignment, but I'm gonna make it due next Tuesday. So on Thursday, I'll finish talking about some of this stuff, and then we'll start talking about some of the VR things. Get myself to the program counter thingy. All right, so questions, comments, concerns, bribes about any of the stuff we talked about today? Okay, well, I will see everybody on Thursday.
See you, Professor Lemon.
Yeah, have a good one.
Thank you, Professor.